Hello, everyone, and thank you for attending today's webinar, Quantitative Analysis and Mapping Combined. Before we begin, I would like to cover a few housekeeping items. At the bottom of your audience console, there are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or if we run out of time, it will be answered later via email. We do capture all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget, which looks like a green folder at the bottom of your screen. You can expand your slide area by clicking on the maximize icon on the top right of the slide area or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now, before we begin, I would like to take a moment to thank Sue Ornell and her great marketing team who make it really easy and enjoyable for us scientists here at EDAX to share our experience and our data findings with the rest of the world. So thank you to all of you who have joined in and to the extraordinary efforts to have brought you here. And now we'll begin with the webinar itself. My name is Tara Nilis, and I'm the Global Applications Manager here at EDAX. Today we'll be talking about quantitative analysis and mapping combined. The official subtitle is a study of statistical analysis in the EDS maps, or the data quality. But really the unofficial subtitle is No Pretty Maps Here. And what we're doing today is we're going to focus on the data quality and the quantitative analysis in the view of a mapping section. By combining two very powerful capabilities, you could take your analysis further. So we'll start with a quick review of quantitative analysis with EDS. And this quote comes from the really the microanalysis handbook, and that's that the analyst must understand the limitations of the technique as well as its strengths to avoid becoming a slave to the CAN system. And what we're doing here today is going through and understanding the limitations of the technique and the strengths and being able to provide an understanding of all of the details that go into both quantitative analysis and mapping so that you as the user could use your knowledge to get the best out of your data analysis. By combining two very powerful techniques, we could take our sample detailed information even further. Many people do quantitative analysis as a starting point for their sample analysis and discovery. So really, if we think about what quant is, it's an integral part of microanalysis, which determines the composition of a material. And if you're a materials analyst, you're probably looking at something like alloys and concentrations, or maybe you're a geologist and you're looking at chemical compounds or formulas. And either way, quantitative analysis with EDS can get you to the information that you're looking for. Mapping is then a further tool to help understand the distribution of that chemical makeup within the material. So you have a sampling area, you visualize the image with an electron image on your microscope, and then you take a chemical image of it and visualize the distribution of the elements present in your material. So one of the things that we like to do in our webinars is to keep it interactive, and we always like to learn more about how people use our systems. So I will start today's webinar with a little bit of a poll, and this is for any user who would like to click one or more of the check boxes. You can actually click as many as apply to you. So what type of analysis do you do? Quantitative analysis, X-ray mapping, or quant-corrected X-ray mapping, and please choose all that apply. And we'll go ahead and give it a minute or so for everybody to submit your response. And this is often a question that we ask at the beginning of our training schools as well, to get a feel for where the distribution of the work is done throughout the real world in our users, the way our users use the system. And so in our poll today, it'll also help us gauge where the focus is. And I'll just give another 30 seconds or so. And for any clarification, you might need quant-corrected X-ray mapping is when you're actually taking each pixel from a data set and doing a quantitative correction on it and then visualizing the quant-corrected results. Okay. So I'll move along to the poll results. Oh, this is fantastic. This is exactly what we're looking for. So it's very apparent that both quantitative analysis and X-ray mapping are important and useful techniques in EDS analysis, but not quite as many people combine those two, and that's a good reason to be on the call today. So very, very helpful information. So quant-corrected X-ray mapping, as you may imagine, is the ability to correct each pixel in the map set with a quantitative routine algorithm for either net intensity or atomic or weight percent, and we're going to get into those details today. So what we'll cover in this webinar is really an educational session, and this is what we like to provide to our users to gain a benefit for attending, for everybody taking an hour out of your valuable time, especially different time zones, is very important. So we want to have you make the most of it. Really, one of the goals is to improve the quality of your data. So if you are doing mapping, and how we can give you the best data possible. And for some of you who are already doing some of these routines, we hope to just share some tips to be able to make your routine workflow a little bit easier, or give you a couple more helpful tools to get your job done. So in the session, we'll cover both qualitative and quantitative basics, and then we'll talk about the considerations for quantitative analysis. There definitely are rules to quantitative analysis. There are some considerations and assumptions that the software and matrix corrections make, and we want to make sure that we understand those rules and we respect those rules. But really, I'm here to tell you, in the applied sciences, what we do is real-world samples, and so take those rules and then translate them into how to solve your real-world problems. You can do that with an understanding of the rules and with an understanding of your samples. And finally, we'll combine these two capabilities and show a basic data set to review the statistical considerations, and then we'll move on to complex examples, which really ramp up the two techniques together. So the basics. Qualitative analysis is really what's in the sample, what's it made out of, what elements are present, or how we do a peak ID on the spectrum. On the spectrum, we also do a peak deconvolution once we've done that peak ID to verify that the elements we've selected are in fact the right elements present. And if we think about it from a graphical standpoint or a spectrum standpoint, it's the x-axis of the spectrum, because each X-ray has a certain energy, a characteristic energy, and that can be referenced. If we move into quantitative analysis, we talk about how much of each element is present, and that does require a correct peak ID, which means that you have to have all of your elements properly identified, do your deconvolution to make sure that you have the proper ID, and then start going through the details for identifying the peak above background or signal to noise, which starts with the background modeling and removal from the quantitative equation. Really everything in analytical chemistry is signal to noise, and even like most things in life are shuffling the signal from the noise, and that's exactly what we do in quantitative analysis as well, and very important here. So what we then do with that peak area is we take the peak intensity within a region of interest, and the region of interest is very important because that defines the x-axis width that we consider a particular element. And so while the y-axis of the spectrum determines the intensity for the quantitative analysis, we still do take an x-axis width or region of energy that characterizes a particular element. Now, we're also talking strictly about standard-less quantitative analysis today. So all of the quant and the mapping we'll talk about standard-less. We do have a link to one of our previous webinars from my colleague Jens, and that covers more details of quantitative analysis itself. And so feel free to use the resource list and watch the previous webinar for an in-depth review of quantitative analysis and some of the considerations with standards. But today will be strictly standardless. So now for some data. So with qualitative analysis with EDS, sometimes we get really lucky and we have a nice, easy to interpret spectrum. You can see here they're all K-lines. They're nice, easy Gaussian-shaped peaks. This is a, looks like a feldspar, and we have pretty easy to identify materials, the aluminosilicates, even the oxygen, low energy, and carbon coating, which we all see there with our nice Gaussian-shaped peaks. And really quickly, I'm going to move into a more complex example for qualitative analysis with EDS. And with qualitative analysis, we have sometimes to do peak deconvolution to be able to really understand what elements are present to get that accurate ID that we need to do for quantitative analysis. And so in this example, I start off with actually the full solution, and your software auto routine will get you really close to the results the vast majority of the time. But here today, we're talking about when you as the user need to put some additional thought into your analysis. And so one of the rules of thumbs is start simple. And so in this case, we'll start with what seems to be an obvious choice, potassium and calcium. And we can see that the light blue line, the peak deconvolution, does not match the actual acquired peaks, the spectra in red. So we move along to a second potential solution, and we've added antimony there, and we could say, aha, that looks like it finally lines up. But with a careful eye, we could actually see that just to the left of that main antimony L peak, we have a peak that is not covered with the blue line. That means that we are missing something. So we add potassium in there, and beautiful. We get a nice series of peaks on that potassium and antimony overlap. And now we'll move on to the titanium and barium area, which is further downstream or higher in energy to the right of the spectrum. And so we look, if we were to model it just as titanium, it's not quite spot on, not as good as we would like. So let's model it as barium, and this is, again, not quite perfect. So lovely, we add the two of them together, and we have a much better fit when we have both of them. And you can see here that this is an iterative process. We often say try modeling it with one element versus the other element to see which is better, toggle back and forth between the two of them, and make your decisions. Very often you could look at a spectrum and get a good idea of whether your peak is proper. And earlier I mentioned Gaussian, and Gaussian is a nice regularly shaped peak, and we can see here the aluminum and the silicon are nicely shaped. And for those of you in the semiconductor or microelectronics industry, you might say, oh, silicon and tungsten is a difficult overlap, so let's model it as silicon just to make sure. And sure enough, that's a nice silicon. And here's our tungsten line. So one of the differences between a K line and an M line is that your M lines are going to have your M beta peaks or your daughter peaks that are a little bit more tightly bound to the parent peak, and that creates a deviation from Gaussian, the higher energy foot of the peak. So we could see if it was tungsten, we could see our tungsten M beta would have a slightly broadened base of the tungsten. Overall, the peak is shifted and doesn't fit well, so we're pretty confident in our silicon solution for that one. Now, let's move on to a more challenging example with an L-line. And L-line series are complex shells where you have many elements buried, often beneath one parent peak, or where you have subsequent series of peaks. And in this case, we'll model it first, again, as the tungsten, and we can see, nope, not quite good. So we model it again as the L line, and this looks a little bit better for our antimony L line, strontium L line, sorry. And then we also add the silicon and the tungsten in as well, and we could see that we have a nice visual looking fit. because those are all tightly bound in together, sometimes we get better assurances when we put up the quantitative results too, and we look at the error percentage. And the error percentage is going to help us sort the signal from the noise and give us a number in net intensity and error difference between whether the peak is actually there, whether it's separated from the background, and by the deconvolution, how much is it separated from the other potential overlapping peaks. And so the error percentage is going to reflect all of those potential sources from error and give you an error percentage. Rule of thumb is if it's lower than about 33%, it's statistically one confidence interval likely to be present in your sample. And so we could see here, while this is a complex example, our numbers help us pretty good. So now that we've covered qualitative analysis and we have a little bit better understanding of our peak shapes and how to use deconvolution to get the correct peak identification, let's move along to quantitative analysis, or really how much of an element is present in each of the samples. And the reasons that we do quantitative analysis is really to figure out what it is. So what are we looking at? What are we sampling? What is our material? What's it composed of? And so here's a pretty easy example of a spectrum with a few different nice Gaussian peaks, calcium, sulfur, and oxygen. And there's also a carbon peak, and this is because that sample was carbon-coded. And so we'll remove that from the quantitative analysis. We have a carbon coding correction function, which really works out nicely because carbon does not only it interferes if you were to include it in the quant results, but there is some absorption that goes through, especially for the light element X-rays that are passing through the carbon coating on their way out to the detector. And so the carbon coding makes up for that really nicely. So we move along to look at the weight percent and atomic percent for this spectrum, and we could maybe see some trend going on here. Let's drop out the weight percent and analyze this as a compound with atomic percentages. And the atomic percentages, if we look at the numbers, we could translate them into atoms. And this is where somebody with experience with their sample or with their interpretation of quantitative results might then start to see where we're going with this. And we could say it's CaSO4, and we might even be able to term it calcium sulfate. And for further information about this particular sample and how to use a database library to understand what the material is or match it to a known material with a library, you can review our Spectrum Match Library webinar and that capability. But for now, we'll move along to considering how we work with quantitative analysis as we start to consider the quant algorithm itself. So a few years ago, one of my colleagues came to see me and he said, Tara, I'm trying to figure out which sample is which. I've got nickel and a silicon sample. And he's like, could you help me out? And I'm thinking, sure, yeah, easy. And I said, I'll just pop them into the microscope, collect a couple of quick spectrum, and tell you which is nickel and which one is the silicon. And he handed me the box of samples, and as it turns out, they were our EBSD standards. And just by sight, we could tell what the silicon is and which one is the nickel. They have distinctive shapes. So I said, oh, this is easy. Don't even need X-rays to analyze this one. We could analyze this with vision and sight alone because we know what our material standards are. But mostly when we analyze a sample, we cannot just simply predict what it is by looking at it. And so in this case, we're looking at a field of view with a sampling area that has both silicon and oxygen. And we're looking at it at 10 keV, also carbon-coded for our carbon peak that we see here. And at 10 keV, our excitation of the electron beam gets us about equal intensity of the silicon and oxygen peaks. And if we say, okay, well, what does that tell us? Are silicon and oxygen in equal percentages? And so the short answer is no, we can't really estimate the weight percent from a spectrum, and that's because what our beam voltage does is it ionizes the material and it creates X-rays, which we then detect. However, there are differences in the ionization potential between different atomic number elements, and there's also different absorption factors. So as those X-rays are leaving the sample, they're subject to absorption based on the other elements that are present. And so at 10 keV, we just by chance happen to have the same peak intensity. But if we move to a 20 keV collection, which is what we have in the outline, we could see that now silicon has more excitation and oxygen has much greater absorption. So there are actually more oxygen X-rays as well. However, they're created deeper in the sample because 20 keV penetrates further down in the sample, and the oxygen have lower energy. They don't escape as well. And this is where, so PCs are capable and competent, but they are not smart. So PCs and algorithms don't actually think for us and say, well, this sample is homogeneous, or these are the elements that are present. And this is why, well, it tells us which elements are present, but it doesn't tell us if they're present in equal amounts. And this is why you, as the analyst, ought not be a slave to the system, as we said in the first slide. So it's important to understand that matrix corrections are required to make the quant more accurate, because that algorithm is depending upon you as the user to have proper input into the system. And so the matrix corrections account for interelement effects. And what that means is how the presence of atoms or X-rays of one element affect the other atoms or X-rays within the sampling area. And they make these assumptions, the corrections make the assumption that the sample is homogeneous, that the sample is perfectly smooth, and that's so that the X-rays that are created, that they interact with all elements in the same amount, and that when they leave a perfectly smooth sample, that they all have the same trajectory towards the detector, so they all have the same escape path. And then also that the sample is infinitely thick to the electron beam, so that the electron beam has the opportunity to equally excite all X-rays of all elements equally. And when we do satisfy these assumptions, the quant results should be within the limits of the technique. And just real ballpark number here, minimum detection limits of about 0.18%. And then we also have a statistical error, which is a standard deviation, which is directly related to the counting statistics, or the number of counts that we're considering in the analysis. And so here's where we start going full speed into statistics. So X-ray detectors detect our X-ray counts in values of counts per second. And these CPS are very valuable to us because we have the ability to alter the CPS. Input CPS is the raw counts that impinge on the detector, and output counts is the number of counts, or the amount of counts per second that have been processed through the electronics, and they're what's making their way into the spectrum or to the maps. That input to output conversion is a function of dead time and amp time. And the dead time is how much time is lost during that conversion process. And we also think of it as how efficiently the input to output conversion happens. And then amp time is the user selectable speed at which we do that conversion. So if you speed up the processor, then your dead time is actually lowered. And so the faster amp times give you lower dead time, which give you better efficiency. However, that comes at the expense of a slight loss of resolution quality. And so that there is the trade-off between speed of conversion and resolution quality. And we'll talk about this in a few slides from now. So N is then the total number of counts for any element of interest, and that's within that energy region of interest. And we use the total counts, or the gross intensity, to allow us the background modeling, or separating the peak from the background, or signal from the noise. However, when we do a quantitative analysis, the CPS is actually a value in counts per second. It's an integrated function, and we basically take snapshots of counts per second. And that's why as the count rate increases, the CPS value, or the net intensity for your quant numbers, doesn't actually change. So, as your count rate increases, your net intensity does change. However, if your collection time increases, your net intensity doesn't change. And so, but what the increased CPS does is it gives us better accuracy. So the more counts that we have, the more collection time, we have a better opportunity to do a better peak to background or peak modeling. And so because the number of counts that we're looking at is important, I'm here to talk a little bit about how we increase the quality of your data by virtue of the N factor, or the number of counts, net intensity. So increased number of counts that you're working with has a smaller standard deviation. And therefore, to increase the number of counts that you're working with, you could increase the collection time. You could also increase the count rate. And again, the increased collection time doesn't actually change the CPS value that's used for the net intensity. However, the increased count rate does change your net intensity that's used. However, increased collection time does give you total number of counts increase, which gives you better background modeling. And of course, you could also decrease your dead time or have a better efficiency of input to output conversion, and that's by using a faster amp time. And so if we consider that the collection spreads the collection time over the entire area, this is going to be important as we start thinking about mapping, because we're dividing a field of view into many, many pixels. So the first part of this study is an analysis of how many counts do we need to attain a quality of collection that we feel is important for data statistics. And in this example, we're working at 10,000 counts per second and 20 kV on a nickel titanium sample. And I'll usually say as a starting point for quantitative analysis, if you're just putting an unknown sample in or even a known sample, a good place to start is 10,000 counts per second. Adjust your kV to proper overvoltage and adjust your beam current to about 10,000 counts per second. And in this case, the first collection was 1 second, and we could see that all elements are identified, and there's a nice peak to background, pretty easy sample, but we see that the background is a little bit grassy, I like to say, distribution. So let's collect for 10 seconds, and we see that that background becomes a little bit more regular. Also, the peaks and the valleys look a little bit cleaner as well. And that's after 10 seconds, and now I'll switch to 50 seconds, and now we've really looked, we could see a nice clean background. And what does that translate to? So in the actual quantitative analysis of this sample, again, this is a nickel titanium sample at 20 kV, and this is a metal alloy composed of nickel and titanium. It contains these two elements at about equal atomic percentages, but the real goal is that it requires a tight compositional control when making this alloy. So the real goal here is to get to a number where you're confident that that number isn't changed. So getting to statistics where we have a reproducible result over and over again. And how do we get there? So we could see the quant results at 1 second, and then we move up to 10 and 50 seconds. So between 1 and 10 seconds, there's a little bit of a variation from about, if we look at the nickel, we're looking at about 60%. And then if we look at 10 seconds, we're looking at about 58%. And after 50 seconds, we're at 58% as well. But what you may notice is that our net intensity has changed just a little bit. And this is, even though the count rate has stayed the same and the net intensity should about stay the same, we could have some beam current fluctuating, but I don't think that's the case in this time. This microscope that I used was very stable for beam current. So what's actually going on here, and I'm taking this opportunity to point out the effect of carbon coating or carbon contamination on your sample, and that's what's going on here. There's actually a change in the net intensity, and that's likely because there's a little bit lesser counts per second in our longer collection time, which is the third of the analysis, and I think that's probably because a little bit of contamination occurred, and so that lowered our overall CPS. By less than 1%, but it's notable here mostly because I'm looking at all of the numbers. And Also, if you have a plasma cleaner, really helpful to use the plasma cleaner to prevent something like this and give you the cleanest sample possible. If you have one, use one. If you don't have one, take a look at them because really helpful for microanalysis. The other reason I'm looking at those numbers so closely is because you may have noticed that these two quant numbers, these concentration numbers, are exactly the same, which, yes, we were shooting for quant numbers that are close, nearly the same. It's very, very, very rare to have quant numbers that are exactly the same to 2 decimal places out. It caused me to question the data, and so I looked at those numbers, the CPS numbers, also the error numbers, and just to make sure that we are, in fact, looking at 2 different spectra, and just by interesting rare chance came out to the exact same quant numbers. Also, I overlaid those 2 spectra, the 10 and the 50-second spectra, and you can see a little bit of difference in the spectrum. The 10-second collection has more of that grassiness in the background compared to the 50-second, which is a little bit smoother. So really, really nice, interesting coincidence that the quant numbers are exactly the same, and that's what we're shooting for here, is consistency, reproducibility. And so taking a little bit further now into statistics, I set up a 100-point auto sample collection, collected for 20 seconds, so somewhere between that 10 and 50, and even up the count rate a little bit to add another variable in. And we could see that the mean is shooting for that 58%. We're right in that same area again, 58% for nickel by weight, and then our standard deviation is really, really nice and tight. And this was actually not the same point. This was 100 different points, slightly different, all within a few microns distance, but nonetheless different sampling points. And so we see that nice standard deviation. This is what I would consider is a really good target for reproducibility on your quantitative results. And so we had 10-second collection time with 10,000 counts per second, and that was about the fast end that got us the good data. Let's look at the analysis in a different way. Let's say, okay, we had 100,000 total counts, and let's skin the cat differently, so to speak. So not 10 seconds at 10,000 counts per second, but let's go for 1 second at 100,000 counts per second. And the goal here is to show you that it's the number, or N, of counts that matters, not necessarily how you go about getting them. And so at 1 second with 100,000 counts per second, nice, we're real close again to that 58 number, that nickel percentage. And one of the other things that you might notice is that our resolution changed a little bit. And a few slides ago, I said that as your amp time speeds up, which it must do in order to accommodate the faster count rate, you lose a little bit of resolution quality. So we lost 3 EV in resolution, but we still have really nice, close to 50% weight percent on our results there. So really, really nice number. And that was just at 1 second collection time. And so now to visit that point and emphasize a little bit more. So as our amp time speeds up, we lose a little bit of resolution quality. Is this going to affect the quality of our quantitative results? And the reason we're here for this webinar is to investigate all reasons why quantitative analysis quality is important in all ways that we can fine-tune our parameters to get there. So let's look at all of our 7 user selectable amp times, going from speeds of 7.68 microseconds all the way speeding up to 0.12 microseconds. And we have a swing of resolution. I hope you could read that there. We go from, I think it's 127 EV all the way up to 156 EV, which is the maximum resolution of this detector. And that detector speed, that 0.12 amp time, that can get you to over 1.5 million counts per second processing. So even at that extremely high count rate, you're still achieving a quality of resolution. How does the spectra look? Well, you could see in that fastest one, we have a little bit broader on the edges or the peak feet here. But by and large, the spectra look nearly identical, nearly exactly the same. And how are our quant numbers for the range of resolutions? And the quant numbers look really good if we go down weight percent. And again, looking at, for ease, looking at nickel and 58%. As we speed up our amp time, lose a bit of resolution. we could still see, even at the fastest amp time, we're still getting in that 58% nickel. And then we even do a standard deviation, and this is the tightest standard deviation yet out of any. So even when you speed up your amp time to accommodate faster counts or lower dead time, we're still getting that real high quality resolution. So no sacrifice of resolution performance when you have when you're speeding up your processor. Okay. So now what we'll start to look at is, now we'll review the quality of the quantitative analysis. And in the preceding couple of slides, we looked at how the number of counts per second in an element peak of interest sets the quality of the collected data. The quality of results increases as the number of counts increases. However, it will plateau at a certain point. And I think we showed that at about 10,000 counts per second and 10 seconds, or 100,000 counts per second and 1 second, we've plateaued. So we've gotten consistent results. And so we keep that in mind as we start applying to mapping. The number of counts can be increased, so you as the user have control over increasing your counts to get that better statistical quality with increased collection time or count rate, also with faster process time or lower dead time. And even at the slight degradation of resolution, you still do not lose the quality in your quant results within about a 30 EV resolution swing, which is the maximum where this detector was performing at. So now we move along to the second factor, which is sample homogeneity. And I'm only going to talk briefly here about sample homogeneity just to set us up for the mapping aspect. Again, for further information about matrix corrections and homogeneity, you can see the full quantitative analysis webinar. So what we're looking at here is how the equation assumes that the sample is the same composition throughout in X, Y, and Z directions. And considering that in a map, each field of view is divided pixel by pixel in X and Y direction. And so what do we mean by sample homogeneity when we look at one pixel at a time? It's how much of the same is the sample from pixel to pixel. And in this case, we look at that same nickel and titanium example, and we say, okay, well, the matrix corrections are assuming that it's homogeneous throughout, and the reason that it does that is because it tries to anticipate the influence of the other element on the first element. So for example, as a titanium X-ray is leaving the sample, it is actually slightly absorbed by the nickel. And that's reflected in the A factor. So Z, R, A, and F are atomic number, the German word for backscatter, absorption, and fluorescence. And all of those will help get the best quantitative results, taking into consideration the other elements present. It's also the reason why peak height is not a good indicator of concentration. And so we see titanium is 40%. However, the titanium peak is higher. Part of that reason is also because better resolution in the titanium peak is lower in energy, so the peak itself is higher. All of these things are considered by the quant routine, so let that good quant routine do its work. And so what makes a sample homogeneous? And to reference that same microanalysis handbook again, it is a small range in variation and composition within a certain tolerance level, and it's also dependent upon beam position, whether we're in spot mode or raster area. And so considering that for mapping, we divide a field of view into discrete steps or pixels or sampling areas. So each of those ought to be homogeneous when we take each pixel's spectra and quantitative analysis for the data. And then we also define it as all points are the same within about 3 times of the standard deviation. So now we move along to the mapping aspect of the webinar. And so in mapping, what we look for is an image that represents the distribution of all the elements or the composition within the field of view. And we see here quite a nice looking map with a beautiful distribution of elements within that map area. But boy, as far as homogeneity goes, we're really in trouble there because that is definitely not homogeneous. And so let's start a little bit easier first. And in our first mapping example, we're taking that same nickel titanium sample, which should be the same throughout. And if you remember before, it's the manufacturing process keeping a tight compositional similarity is important. So whether between sampling area to sampling area or from sample to sample, different samples, or from batch to batch, or raw material to raw material, or lot to lot, or end material, we want to make sure that all of those areas are the same. Compositionally, it's the same throughout. So now we use a map as a sampling area with about 50,000 data points because a 256 by 200 map has many pixels, which we could use as our sampling point. During the collection, we raster at 200 microseconds per pixel, and this one was collected for 11 frames, which is about 2 minutes at 100,000 counts per second, yielding about 2 counts per pixel per second into each of those pixels in the map. And when we look at the sum spectrum, which is the cumulative spectrum from all of the pixels together, we see we're really spot on. We're nice there with our 58% for our nickel. However, if we look at just one individual pixel, that's not so great. We have a really sparse spectrum, and the numbers are off. So what we can then do is just bin a few pixels together. So now we're looking at 9 points together, and we come back in line at about 58%. So it's really about the collection and using the data wisely. So if individual spectrum is not giving you the quality that you need, you can bin more points together. Or the next step we could do is collect for a longer amount of time, and this one was done for 58 frames for 11 minutes at the same count rate, and we could see the variation is less and it's getting us closer. In the interest of time, I'm not going to review this one completely, so we'll move along to an even longer collection time of 45 minutes, and in this case now, we could see that the sum spectra again yields that same quality of 58% that we're looking for. But now a single individual pixel and one spectrum out of those 50,000 spectra from that map, one spectrum gets pretty close, and our mean is pretty close to 58%. We do see out of 12 randomly selected points that there is an outlier. And when we remove that outlier, our mean and standard deviation are a little bit more reasonable. Now, removing an outlier is a question sometimes in statistical analysis. Sometimes people want to do it. Sometimes people don't want to do it. And so if you don't want to do it, then the next solution would be to collect for a long time, or longer time. But the point here is that you can get pretty close to what your target is, even after about 45 minutes, but you will have outliers, and that's because of that greater deviation. And so if we then collect for a longer amount of time, and now we've really gone up to 6 hours collection time, and in this case we have a much more stable set of quantitative results, which we'll see in the next couple of slides. But the first point here is you could actually visualize just by the map itself when you do a weight percentage correction for each pixel and set, we could actually visualize less distribution in the 6-hour map. So altogether, it looks a little bit cleaner. If we look at the numbers themselves, so we pull out 10 randomly selected individual pixel sampling points out of the 6-hour map, we could see that there's no outlier this time. And but really, with the outlier removed from the 45, it's about the same. So the difference is that your very long is going to get your quality consistently. And the wonderful thing about mapping and sampling points is software and computers work really, really fast. So for all of those 50,000 data points, we could do that ZAF equation for each of them. We could break every pixel down into a spectrum, elements, and quant results, and come up with an Excel spreadsheet that has cells which represent those quant numbers. And I've just made a little overlay here. This is only a snapshot of the 50,000 numbers that are actually in each of the maps. And so by polling all of that data, what we come up with is the 45 minutes has a mean of 57.4 with a broader standard deviation. We can see that definitely there's a wider distribution. And in order to get a better number more consistently, we want to collect for a longer amount of time. And it's for you as the analyst to decide what is the best set of conditions, collection times, and parameters for your particular goals. And finally, on this sample, just make a few notes about what you could actually do for image analysis. This is a point of sometimes question. It's pretty easy to enhance an image, and the first way I did it was just using the PowerPoint functions of brightness and contrast, and we could make the 45-minute map look a little bit nicer. We do a EDAX image scaling, which actually takes the data and looks at what the range of values are. We could use the full number of gray levels or color levels that are broadened within a slightly larger range within the min and max values for the concentration. So we're basically scaling our 250 colors between, I think that's 45 and 59 or something in there. So we can see the image on the right scaled up looks a little bit less variable. And when we do it for our 6-hour map, we have a much, much cleaner looking image, again, because there's less variability in this, less swing, less standard deviation. And when we use our image scaling, we do much better on our appearance. So to summarize our sample homogeneity example, we divide our maps into pixels, each one being a discrete sampling point, and quick maps can yield usable quant data, especially when binning or summing a few pixels data together. Longer maps with about 5,000 total X-rays per pixel yield reasonable results, but have outliers. And if you really want the highest quality results with both target values and less standard deviation or variability, then you want to go for a longer collection time. Of course, you could go for even higher count rates, so that's up to you as the analyst to decide. And just a note about integrated EDS-EBSD analysis. Someone doing EBSD analysis combined with EDS would probably shoot for something like this. So about the 5,000 X-rays per. So now we'll keep it interactive as we go into the last about 10 slides of the presentation, and we'll go into some more of the complex examples. So we did the easy stuff, and now I want to ask you, the audience, do you frequently map or run into samples with greatly different atomic numbers? So for example, iron and carbon or lead and oxygen, where you have a heavy atom and you have a low energy X-ray leaving in between those heavier atoms. And the reason that those are more difficult is because those low energy X-rays are heavily absorbed or lost within the sample. And so that makes a much more complex example for both quantitative analysis and for mapping. So just kind of an idea. Do you as the users run into examples where you have a big range of elements present? Wonderful, good, excellent. So the point here, if you do run into these types of samples, you really need ZAF, weight, and atomic percent corrected X-ray maps. And here's how we do it. So we're using a tungsten carbide example now, and that's because this is just a great example of a heavy element and a light element, low energy X-ray. And so tungsten and carbon, carbon being our low energy X-ray, and it's got to leave through the presence of those big tungsten atoms that are in the way. And you could see, well, first off, so tungsten carbide is a compound with about an equal number of carbon and tungsten atoms. So our atomic percent is 50-50. So shouldn't they have equal representation? Well, no, of course not. We already learned that peak height is not a good way to determine the concentrations. We really need to depend on that ZAF equation. And so looking at those peak height differences, they are much more different when we consider the weight percent, not the atomic percent, so not the compound. The weight percent difference between carbon and tungsten is about 6% to 94%. So no wonder why carbon is really easily lost within our spectra and also within our maps. And so if we do the numbers, a little bit more of a complex example. So if we could see our absorption factors, our carbon is heavily absorbed in our material, and so our mathematics need to work much harder, and our correction and perfect algorithms need to work even more. And so what we want to do then in this case is even refine the data a little bit further, and we have just the tools to do that. One note is that cobalt is in some areas and not in some areas. It's left in here because it's a non-homogeneous sample, which we'll see. Okay, so how do we refine the data a little bit more to get exactly precise? So we use a background correction. And so by being able to select our background areas manually, you might be able to see in this area right here, the background isn't fitting so well, and that's definitely affecting the ability to detect the carbon signal. So let's create our own manual background point, and now afterwards our results are really nice 50-50, really close to that 50-50 result. So before they were 48-52, after they're 49.9 to 49.7, the remainder going to cobalt. And so now it's obvious we're looking at a non-homogeneous sample. For the interest of spectrum, we're collecting from an area within the tungsten carbide itself, but now we see a distribution. And so taking a few different background points, a few different collection times to be able to say, okay, 10 seconds versus 100 seconds, and we're still doing good even at the 10 seconds. We're getting that nice good atomic percentage with background manually corrected and applied over and over again. This example shows why we don't want to go to severe overvoltage or high beam voltage, high accelerating voltage, and that's because now the matrix correction factors would have to work even harder. The beam penetrates deeper. That means the X-rays are generated further down in the material. That means the low energy carbon has a greater escape path to travel to and more absorption factor. And now we're looking at about only 20% of our X-rays for carbon getting through to our detector versus about 33 before. So really we want to find that correct overvoltage, a little bit lower beam energy. And now we map at 8 kV. And even at 8 kV, the carbon peak is small, as we saw. So if we're only looking for the peak intensity, the carbon is definitely underrepresented. So these areas, these square areas, you can kind of see the crystal shape from the tungsten carbide, the faceted areas. These are the tungsten carbide areas. We really we're not seeing carbon here. We're only seeing carbon in some of the what turns out to be voids that are filled with carbon or are diamond material, as it might be. So we're not seeing carbon at all where the tungsten is. So it doesn't even look like it's tungsten carbide when we're looking at just the net intensity map. So we do a weight percent corrected map, and really not much better because, as we mentioned before, by weight percent, carbon is only 6%, and so tungsten sure gets the visual representation when we look at it by weight percent. And here's where it's really important to have a full atomic percent correction factor for each pixel in the map set and display the pixel color intensity that represents the atomic percent. And now with an atomic percent of 50-50, our atomic percent maps for carbon are finally visible to see the carbon within the map area, making it truly a display map of the atomic percent and the compound formula for the tungsten carbide. And on a final note, we could also do this with a phase map. So by phase maps, which look at each spectra individually and break out different phases, we could give an intensity for just the tungsten carbide phase and omitting the high intensity hot spots from the carbon-rich phases. So in conclusion for our map our quant mapping corrections, we could see that matrix corrections correct the quantitative data, especially when there are atoms of widely different types. So the tungsten carbide, or maybe the lead oxygen, or iron carbide. When you are mapping types of samples, you really want to use those full corrected weight and atomic percent. So atomic percent gives better representation to the lighter elements whose peaks are smaller and have a low weight percent contribution. And really what you get is a truer view of the compound formula. And I'll also make note that we do have quant mapping with standards, which will even refine your data even further. And in final conclusion, to look at quantitative and mapping combined, we could see that the quality of the quant results is dependent on the statistics, the number of counts that you get for the calculation. And by increasing the statistics, you improve the quality, but only up to a certain point. And it's at that certain point that you want to find where you then apply it to the quantitative analysis on the pixels from each individual sampling point in the map, making quant map feasible. The quant map equation, or the quant equation, relies upon the matrix corrections for the interelement effects, but when you apply it to mapping and do each pixel individually, each pixel we can assume has a certain level of homogeneity that's tolerable for the correction. And by using the tools of weight percent and atomic percent maps, you can get the most accurate visualization for your quantitative analysis, even on some of those real challenging samples. And so now I will wrap it up with questions and answers, and also a view of my email. So for any of you who want to take notes and get a hold of me afterwards, you're certainly welcome to do that. We'll get back to you via email. And so great first question. Thank you, Sue, for getting the questions over to me. The question is, does increasing the process time decrease the dead time? So the answer is that speeding up the process time does decrease the dead time. That's exactly right. By going faster, by pushing the processor faster, you decrease the dead time, or the amount of time lost. And so that's going to increase your collection efficiency. That'll give you more counts at the slight loss of resolution, but as we saw, within about 30 eV, even at the fastest amp times, you're not losing any of the quality. So a faster process time is very useful for decreasing your dead time. Yeah, can we fit, hi, hon. Can we fit the carbon peak well? Very good question. Carbon is a very challenging peak to fit. The deconvolution below 1 keV is more challenging. The carbon background regions are very, very important to help get the best peak shape fit for carbon. And in that tungsten carbide example, even just a little bit of adjusting the background will help better fit the carbon peak. The other thing with carbon is that sometimes you might see a peak shift due to incomplete charge. The EDAX team software has a ICC correction for it underneath the process area, and you could activate that, and that'll help accommodate for that ICC shift. If you need help with that, just give one of us a holler here. And again, that's on the spectrum process ICC correction. Let's see. Optimum kV for mapping and the optimum time for mapping. So the important factor for kV is that you want to get the overvoltage just right. And we generally say about the beam kV should be about 2 to 3 times the energy of the highest element of interest, highest energy X-ray line of interest. And that's because we are looking at getting enough X-ray excitation for that higher energy line. Of course, if you're looking at, say, the tungsten M line, that's a little bit lower in energy, or a lot lower in energy compared to your tungsten L line. And so you can, say, work at that 8 kV that we did for the tungsten carbide. So about 2 to 3 times the highest energy line of interest. And then the collection time is really a matter of getting enough statistics to have a quality result. In our example, we saw that 100,000 counts per second, somewhere between 45 minutes. 45 minutes got us a nice mean value, but we had some outliers. Collecting for a longer time is going to decrease the range of standard deviation. Great questions. And for any of you who leave right at the turn of the hour, I'll say thank you all for attending. I'll continue to answer questions, but I want to make sure I thank everybody who attended. It's a lot of fun working with everybody and the good questions. So keep them coming. Next question is magnification a factor, and how high can it be? Great question. And that's because, like in the electron microscope, it's easy for us to lose the concept of scaling because, we visualize something, that we can hold in our hand and we get an idea of scale, or we could magnify it 2 or 3 times when we zoom in our iPhone or look under the optical microscope, and we still get an idea of scale. But an electron microscope, we can easily zoom in 100,000, 200,000 times, and then we start losing that concept of scaling. So what's important with magnification is the volume of interaction of the X-ray generation. And that volume of interaction is dependent upon beam KV, anywhere from a few tens or hundreds of nanometers to a few microns spread at the higher 20 keV or so, especially for the lower atomic numbers. So you could use a Monte Carlo simulation, electron flight simulator package to figure out what that volume of interaction is. And you want to make sure that you're scaling your magnification accordingly to get as close to that volume of interaction. The reality is most people are looking at features that are finer than that volume of interaction. And so to work with real world work, we just have to understand that there's going to be a distribution. Sometimes your X-rays are going to be coming from areas that are much larger than just the pixel itself. And so the matrix corrections will have some influence on that, or be influenced by that volume of interaction. Okay, let's see. Hi Frank. Accelerating voltage. Oh, for a starting analysis on a totally unknown sample. My rule of thumb, my personal rule of thumb, is 15 kV for a geological material and 20 kV for a materials, metal alloy type of sample. And those are, if it looks like it's something that's going to charge, if it's completely unknown, I would put it in low vac also and hope that the 15 kV would be okay for it. I also check out the ending point of the background, or the Dwayne Hunt limit. So if I'm putting 15 kV in, am I getting 15 keV at the tail end of my spectrum? That tells me, is it tolerating the charge okay? And so that would be a good starting point. And then from there, I look at what the highest energy line is, and then say, okay, well, could I go down lower in energy? So for example, if I put like the tungsten carbide in, I might have started at 15 or 20 kV, and I saw, oh, I could work with the tungsten M line, so let me ramp down to 8 kV, minimize that volume of interaction, which keeps that the sampling area smaller. And why not use 4 kV for tungsten carbide? Very good question. So 4 kV would be just about the exact right over voltage, and for quantitative analysis, that would be a really good set of conditions. I used 8 kV because in generally, rule of thumb, I find 8 kV on my microscope gives me a good amount of count rates without having to increase my beam current too much. So I tolerated the over voltage, which means that we're going to get some, we're going to make the quant correction factors, the ZRA and F factors, work a little bit harder. The math is going to have to work harder. But I got a higher count rate, so what I gain in statistics is made up for in the math. Samples with topography, and I think there were a couple similar questions. How accurate is the chemical analysis for powders or samples with high topography differences? Great question, and the reason it's a great question is because it changes the escape path. So from one side of the particle is facing the detector, the other side is facing away from the detector, so you have different escape paths towards the detector, which means that your low energy X-rays are not going to be as efficiently getting to the detector when they're on the far side, and they're going to be underrepresented. The matrix correction factors don't account for that topography. It's impossible. It can't do it. It doesn't see how rough it is. So a few things that we can do, we use our CPS map. So our CPS map is a visualization of the topography of the sample, which shows the changes in count rate. Say from the far side of a particle might be darker, and the closer side towards the detector might be higher, and that's because the CPS map is actually a representation of the count rate. We could also correct for that on an individual spectrum itself by using a routine that we call PB-ZAF, or rough surface particle ZAF correction, and that is a spectrum quant correction. And so, the effect, what is the effect of the skirt effect on mapping in low vac mode? Very, very good question, especially on a non-homogeneous sample. And we've seen that the beam skirt could even be a few millimeters in distance away from the intended point where the beam is placed. So you will get diffusivity as your pressure goes up inside the chamber, and you'll get wider and wider sampling area by nature of that skirt. For spectra themselves, we could correct for that by collecting spectrum from two different beam pressures and extrapolating out the high vac spectrum, and that works extremely well to eliminate the elements that don't belong in there, that are outside of the sampling area, as well as getting the proper quant results for the elements themselves that do belong there. And but as far as mapping is concerned, you want to increase, you want to make up for that issue by increasing your statistics, because the majority of counts are coming from the intended sampling area. So with more collection time or higher count rates, you're going to get better intensity on the counts where they belong. Can I remind you of what R is in Z, R, A, and F? If I was my colleague Jens, I might be able to say it better, but R is the German word for backscatter, and so the R factor in Z, R, A, and F stands for the German word for backscatter. It is a backscattered correction factors. Let's see. Another question is, if we quantify based only on K-lines without the L or M, the quantitative analysis is still okay? Or the question is it still okay? And the answer is, it is still okay if you have the proper overvoltage. That's a little bit more than 2 times the energy of that X-ray line. Okay. So I'm afraid I might have to wrap up the questions here. Really, really good question. Maybe the last one here is one on the silicon nitride window. I'll just answer this last question, which is, can you comment on the benefits of using silicon nitride window compared to polymer for quant of low Z materials? And 2 comments. The first comment is that our correction or Fano factors for detector efficiency have been updated. So the new detector windows are fully accounted for in our quantitative results. And how does it improve the results is by nature of better transmission of the low energy X-rays. You get more statistics. More statistics leads to higher number of counts, and higher number of counts gives you better quality of your quantitative data. Okay. So with that, I will end, and we will wrap up this session. Thank you very much to everybody who attended, and we look forward to having you in on the next one. Thanks to all of our support team here at EDAX who helped make the webinar possible. Bye-bye.